Test time scaling has become the standard way to push large language models past their training limits. The idea is straightforward. Generate a batch of candidate solutions, then pick the best one using re-ranking, self-verification, or majority voting. In theory, this should work beautifully. In practice, it consistently hits a wall. The wall isn't compute. It's diversity. Standard stochastic sampling, temperature adjustments, and heuristic filters like top P or min P are great at producing different words. But they're terrible at producing different thoughts. When you sample multiple times, you're usually just getting surface-level lexical variation around the exact same underlying reasoning path. If the model's core logic is flawed, or if it gets stuck in a systematic failure mode, generating 50 candidates won't save you. You just get 50 highly redundant wrong answers, and your pass at K efficiency collapses. Researchers have tried to fix this with structured search like tree of thoughts, or logit-level steering like contrastive decoding. But structured search introduces massive latency overhead, and heuristic constraints mostly reshape the token distribution without actually pushing the model into genuinely novel semantic regions. We need a decoding strategy that can efficiently encourage novelty in the model's internal reasoning behavior, not just its vocabulary choices. That's exactly what exploratory sampling, or ESamp, solves. The core insight borrows directly from reinforcement learning, specifically a technique called random network distillation. The observation is simple but powerful. Neural networks make highly accurate predictions on mappings they've seen before, and they struggle with prediction error on novel ones. ESamp flips this property into an exploration signal. Instead of operating in token space, it operates in the model's continuous representation space. Here's how it works under the hood. During generation, ESamp introduces a lightweight module called the Latent Distiller. This is a small multi-layer perceptron that's trained online, at test time, to predict the deep-layer hidden representations of the LLM, using only the shallow-layer hidden representations. In practice, it takes the hidden state after the first transformer layer and tries to predict what the hidden state will look like after the final layer. As generation progresses, the distiller continuously adapts to the representation mappings induced by the current context. Familiar mappings yield low prediction error. Unfamiliar, underexplored mappings yield high prediction error. That prediction error becomes our novelty signal. But how do we actually use it to guide sampling? The authors frame generation as a KL-regularized policy optimization problem. The objective is to maximize the expected novelty reward, while keeping the new policy close to the base model's original distribution. Mathematically, that looks like maximizing the expected reward minus an alpha-weighted KL divergence from the reference policy. When you solve that objective, you get a clean closed-form solution. The new sampling distribution is just the base model's probability distribution, reweighted by an exponential function of the novelty reward. In practice, they approximate this by projecting the distiller's prediction error into the vocabulary space, using the frozen language modeling head. They define the intrinsic reward as the log likelihood ratio between the reference logits and the distilled logits. Substituting that into the optimal policy equation gives us the final sampling distribution. But the most useful way to think about it is in logit space. The new sampling logits are a linear combination of the reference logits and the distilled logits, scaled by an exploration strength hyperparameter beta. Specifically, logit new equals 1 plus beta times logit reference, minus beta times logit distilled. Let's break down what that actually means geometrically, because this is where ESamp shines. The difference between the new and reference logits can be decomposed into two components. First, the Euclidean norm of the latent error vector. This quantifies the magnitude of novelty. A large error means the current context is substantially different from previously explored regions, signaling strong exploration. Second, the cosine similarity between that error vector and the tokens embedding weight in the language modeling head. This acts as a directional guide. By promoting tokens that align with the error vector, ESamp steers generation towards semantically distinct trajectories, not just superficial lexical swaps. It's actively penalizing recurring semantics, not just frequent tokens. There's another critical advantage that emerges when you run this in parallel. ESamp is designed to work with a batch of K sequences generated simultaneously. Because the distiller is updated online using hidden representations from all sequences in the batch, it acts as a shared coordination channel. It functions like a first-come, first-served scheduler. When one sequence explores a latent pattern, the distiller learns that mapping. Suddenly, that semantic region becomes highly predictable to the distiller, which suppresses the probability of subsequent sequences revisiting it. This forces the collective generation to diverge and cover the semantic space efficiently, without requiring expensive cross-worker communication or explicit heuristic penalties. Now, theory is one thing, but running an online training loop and a forward pass inside a decoding step introduces a massive engineering challenge. You can't afford to stall the main generation stream for backpropagation or heavy matrix multiplications. The authors solved this with a carefully designed asynchronous pipeline. The distiller's inference is triggered immediately after the first transformer layer. While the host LLM executes the middle transformer layers, which are often memory bandwidth bound, the lightweight distiller computes its prediction in parallel. In typical settings, the distillation logits are ready before the LLM reaches the final layer, so logit fusion happens without stalling. The training step, meaning the backward pass and weight update, is deferred entirely to the post-processing interval. This is the phase where the GPU is often idle, because the system is handling CPU-bound tasks like sampling, detokenization, and scheduling. By decoupling the distiller from the critical token generation path, ESamp incurs negligible latency overhead. In standard serving scenarios, the throughput penalty is less than 2%. Even under heavy test time scaling with 16 samples per request, the overhead stays under 5%, with optimized implementations pushing it down to around 1.2%. The empirical results validate the approach across multiple domains. On mathematics benchmarks like AIME, science benchmarks like GPQA Diamond, and code generation like Live Code Bench, ESamp significantly boosts pass-a-K efficiency. It consistently matches or outperforms strong stochastic and heuristic baselines, but with a crucial difference. It does so with a much smaller sampling budget. On reasoning models, ESamp achieves performance comparable to baseline methods at pass at 64 using only pass at 8. It also breaks the traditional trade-off between diversity and coherence. Metrics like the Venn score and pairwise cosine similarity show that ESamp generates semantically distinct candidates while maintaining high linguistic quality. It's not just generating random hallucinations, it's finding genuinely valid, diverse reasoning paths. Why does latent space exploration beat vocabulary space? The authors ran ablations comparing ESamp to a vocabulary space distiller that tries to learn novelty directly over the discrete token distribution. That approach was unstable and underperformed significantly. The reason is straightforward. Learning over a high-dimensional discrete vocabulary distribution is noisy and sensitive to tail probabilities. Operating in a compact, continuous representation space makes the online distiller far more stable, and the prediction error carries far more structured information about the model's actual reasoning trajectory. ESamp also plays nicely with other test time scaling techniques. It's naturally composable with temperature scheduling methods like FIRE, and it remains compatible with self-consistency aggregation. Since ESamp operates during decoding to expand candidate coverage, and self-consistency operates post-generation to aggregate answers, they target different bottlenecks. Combining them consistently improves coverage at larger sampling budgets. The takeaway here is that test time scaling isn't just about generating more tokens. It's about generating different thoughts. Standard sampling leaves the model trapped in its most probable semantic neighborhoods. ESamp uses online latent distillation to measure novelty in the model's internal representations, reweights logits to push generation into underexplored regions, and coordinates parallel sequences through a shared distiller, all while running asynchronously to keep overhead minimal. It's a practical, mathematically grounded decoding strategy that finally aligns test time compute with genuine semantic exploration. If you're working with reasoning models, code generation, or any task where candidate diversity directly impacts solution coverage, ESamp is worth integrating into your inference pipeline. The code is already open-sourced in the tLLM framework, and the asynchronous design means you can deploy it without rewriting your entire serving stack. Test time scaling is moving from brute force sampling to intelligent exploration. ESamp is a clear step in that direction,